Hey everyone, and welcome back for another deep dive. You know we love getting our hands dirty with some really fascinating research, and today we're going to be tackling superconductivity.
Ooh, that's a good one.
It is a good one, and you know it's funny because you sent this research over to me, and I was like, huh, superconductivity.
Yay.
It's like one of those things that you hear about and you're like, oh yeah, superconductivity, that's pretty cool, but I don't really know much about it.
Yeah, it's one of those like buzzwords. You
Yeah.
hear it thrown around,
Well,
but
what is it really?
yeah,
And this paper that you sent over, it's dense.
it is dense.
I'm not going to lie, it's a dense paper,
Mm-hmm.
but it's so interesting, and we're going to really break it down, and I think by the end of this, all of our listeners are going to have a much better grasp
I hope so.
of superconductivity and just like all the implications of it, because it's pretty mind-blowing.
Absolutely. It's really a cornerstone of condensed matter physics.
Yeah, so let's start with, before this paper came out in 1957 by Bardeen-Cooper and Schrieffer,
Mm.
BCS theory, before that,
Yeah.
what did we know about superconductivity, or like what were scientists even struggling with?
Well, superconductivity itself was discovered in 1911.
Okay.
So quite a while before the theory came around to explain it.
Right.
And it was this really weird phenomenon where you could get materials to conduct electricity with absolutely zero resistance.
Yeah, it's like it flows forever.
It flows forever.
Yeah.
And so there were a few theories floating around at the time trying to explain it. People were looking at things like fluctuations in the electron density,
Right.
but none of them were really quite getting at the heart of what was going on.
Right. So we had this phenomenon, and it was like, cool, this happens, but we have no idea why.
Yeah, it was just like an observation, like
Yeah,
what
right.
is going on here?
So then this paper kind of comes in, and it's like, boom, here's the explanation.
Exactly. This is the explanation.
Okay, so what did they figure out?
Well, one of the big things that was really important in leading up to this theory was the discovery of the isotope effect.
Okay, the isotope effect.
So
Break that down for me.
basically, they found that if you change the mass of the atoms in a superconductor,
Okay.
so the atoms are made up of, protons and neutrons and electrons.
Right.
If you change the number of neutrons,
Yeah.
so you change the mass of the atom,
Yeah.
you actually change the critical temperature of the superconductor.
So like if you have a heavier atom,
Heavier atom, lower critical temperature.
whoa, okay.
Yeah.
Interesting.
And that was a really big clue.
Yeah, because why would the mass of an atom affect like the flow of electrons?
Right, exactly. And that was the thing that was so perplexing.
Right.
And so this suggested that somehow the vibrations of the atoms in the material were
Yeah.
actually playing a role in superconductivity.
So we're talking about phonons, right? Those little tiny vibrations.
Exactly, phonons. Those are
Yeah.
the key. And
Yeah.
so this is where BCS theory comes in. And it basically says that these phonons, these little vibrations, can actually create an attractive force between electrons.
Wait, hold on now. I thought electrons, they repel each other.
Yeah.
They're both negatively charged.
They should.
So how are they attracting each other?
Well, this is what's so crazy about BCS theory is it says under very specific circumstances and certain materials at very low temperatures,
Okay.
this interaction with the phonons can actually overcome that repulsion.
So the phonons are like little tiny matchmakers.
They're like little Cupid.
Yeah, bringing the electrons together.
Exactly. And these electrons, when they pair up, we call them Cooper pairs,
Cooper pairs, okay?
named after Leon Cooper,
Got it.
one of the authors of the theory.
Okay, so we've got these electrons, they're pairing up, they're forming these Cooper pairs, but how does that lead to zero resistance?
Well, when the electrons are bound together in these Cooper pairs, they basically become a collective entity.
Okay.
They stop behaving as individual electrons and they start behaving as this kind of unified group.
Right.
And this has all sorts of really interesting consequences.
Okay, like what?
Well, one of them is that it creates what's called an energy gap.
An energy gap.
Yeah, so when the electrons are paired up, it takes a certain amount of energy to break them apart.
Okay.
And so this creates a gap in the energy levels that the electrons can occupy. And this energy gap basically prevents the electrons from scattering off of impurities in the material,
Got it.
which is normally what causes electrical resistance.
So it's kind of like they're just gliding through.
It's gliding through
Yeah.
like a figure skater on perfectly smooth ice.
Okay, so that explains the zero resistance part.
Yeah.
But I remember you were saying that there were other things about superconductivity that were kind of mysterious.
Right.
And that this BCS theory helped to explain, like, what else was going on.
Well, one of the really weird ones was the Meissner effect.
Okay, the Meissner effect.
So the Meissner effect is this phenomenon where superconductors actually expel magnetic fields.
So they're like magnets, but they push other magnets away?
They push other magnets away. Exactly. So if you bring a magnet close to a superconductor, it will literally push the magnetic field lines out.
That is so weird.
It's super weird.
So they're not only good conductors of electricity, they're like masters of magnetism, too.
Exactly.
Yeah.
They can control magnetic fields in a way that no other material can.
Okay, so how does BCS theory explain that?
Well, basically the theory shows that these Cooper pairs, when you apply a magnetic field, they all act together in a coordinated way to create their own magnetic field that opposes the external field.
So they're like creating their own little force field
Exactly.
against the magnetism?
They're like a microscopic army pushing back against the invading magnetic field.
So the Cooper pairs are like little magnetic warriors.
They are.
Protecting the superconductor.
Exactly. And that's why the magnetic field can't penetrate very far into the material.
Okay, so we've got zero resistance.
Yeah.
We've got this Meissner effect. Anything else that BCS theory helps to explain?
Yeah. There were a couple of other things that were really puzzling to scientists before this theory came along. Okay.
One of them was the nature of the transition into the superconducting state.
Okay.
So when a material becomes a superconductor, it's not like when water freezes into ice where you have this abrupt change.
Right.
It's a very smooth, continuous transition.
Okay.
It's called a second-order phase transition.
Okay.
And BCS theory was able to account for this smooth transition.
Okay.
And then, remember that isotope effect we were talking about before?
Yeah, the heavier the atom, the lower the critical temperature.
Exactly. Well, BCS theory was able to explain that too.
Okay.
It shows that the heavier isotopes lead to weaker phonon interactions.
Okay.
And that, in turn, affects the formation of the Cooper pairs and lowers the critical temperature.
So all of these things kind of like fit together?
It all fits together in this beautiful, elegant theory.
So it's not just explain, it's like predicting too, right? Like it's saying, if you do this, this will happen. And then scientists are like, oh, wow, it does.
Exactly.
That's pretty powerful.
With a huge validation for the theory. Yeah. Okay, so we've talked a lot about the theory. We've talked about like the science behind it.
Right.
But let's talk about the impact.
Yeah.
Like, how has this theory influenced technology? How has it, like, what are the real world applications of this?
Well, I mean, you know, MRI machines, maglev trains, these are all based on superconductivity.
Right.
And this theory has basically paved the way for these amazing technological developments.
So this is not just like a cool scientific idea.
Right.
This is like actually impacting people's lives.
Absolutely. It's having a real world impact. And as we delve deeper into the implications of BCS theory, the possibilities seem almost endless.
Okay, well, let's delve deeper then.
Let's do it. I mean, it really is amazing. Like, you think about something so tiny like electrons pairing up.
Right.
And it has these huge consequences. Like, we can build these incredible machines.
Yeah, it really highlights how, like, everything's connected, right?
It does.
Like, what's happening at the tiniest level can impact these huge macroscopic things.
It's like the butterfly effect, but for physics.
Yeah, exactly. Okay, so you mentioned before that BCS theory was able to predict some pretty specific things.
Right.
Like the specific heat of superconductors.
Yes.
So first of all, like, what is specific heat?
Okay, so specific heat is basically a measure of how much energy a material can absorb as heat.
Okay.
So, like, if you apply a certain amount of heat to a material, how much does its temperature go up?
Got it.
That's basically what specific heat tells you.
Okay, and how does that relate to superconductivity?
Well, it turns out that the formation of these Cooper pairs actually has a big impact on the specific heat.
So, like, how can electrons pairing up affect how much heat something can absorb?
Well, think about it this way. Remember we were talking about that energy gap?
Yeah.
It takes energy to break those Cooper pairs apart, right?
Right.
So when you heat up a superconductor, some of that heat energy goes into breaking those pairs.
So the Cooper pairs are like little heat sponges?
Exactly. They're soaking up some of that energy.
Right.
And that means that the specific heat of a superconductor is going to be different from a normal metal.
Okay.
Especially at temperatures below the critical temperature where the Cooper pairs are forming.
So BCS theory was able to predict this difference.
Yes, it was one of its big successes.
Okay, that's pretty cool.
It predicted a very specific shape for the curve of specific heat versus temperature.
Yeah.
And the experimental data matched up perfectly.
So that was another point for BCS.
Another point for BCS, exactly.
Okay, so we've got specific heat. What about that other thing? You mentioned the penetration depth.
Right, the penetration depth.
Remind me what that is again?
Okay, so remember we were talking about how superconductors expel magnetic fields?
Yeah, the Meissner effect.
The Meissner effect, exactly.
Like little magnetic warriors.
Exactly. Well, the penetration depth is basically a measure of how far a magnetic field can actually penetrate into a superconductor before it gets completely expelled.
Okay, so it's like how far the magnetic field can kind of sneak in.
Exactly.
Before the Cooper pairs are like, hey, get out of here.
Yeah, exactly. They're like forming this barrier.
Right.
And BCS theory was able to predict this penetration depth.
Oh, wow.
It showed that it was directly related to the energy gap.
So a bigger energy gap means a smaller penetration depth.
Exactly.
Interesting.
So the magnetic field can't penetrate as far.
Okay, so BCS theory's got a lot going for it.
It does.
Explains a lot of different things about superconductivity.
It brought together all these different pieces of the puzzle.
Right, and what's really cool is that it's led to all these amazing technologies.
Absolutely.
Like you said before, MRI machines, maglev trains.
Right.
But it sounds like we're just scratching the surface of what's possible.
Oh, yeah. We are definitely just getting started.
So what's next for superconductivity research?
One of the big things that people are really excited about are these high-temperature superconductors.
High-temperature superconductors.
Yeah, so remember how we were talking about how superconductivity usually happens at these really low temperatures?
Mhm.
Well, these high-temperature superconductors, they can become superconductive at much higher temperatures.
So like how high are we talking?
Well, still pretty cold,
Okay.
but much warmer than traditional superconductors. We're talking like liquid nitrogen temperatures.
So not room temperature yet.
And not room temperature yet, but we're getting closer.
Okay, and why is that so exciting?
Well, think about the applications. If we could get superconductivity to work at room temperature, I mean,
Yeah.
that would be a game changer.
Like what kinds of things could we do?
Well, for one thing, we could have power lines that transmit electricity with almost no loss.
Wow.
That would mean massive energy savings.
Yeah.
And it could revolutionize our entire power grid.
That would be incredible. What about electronics?
Electronics, too. I mean, imagine computers that are like 1,000 times faster
Wow.
and use way less power.
So this is like the future of technology.
It is the future of technology.
Okay, so high-temperature superconductors are clearly a big deal.
They are.
But does BCS theory apply to them?
That's the million-dollar question.
Okay.
So BCS theory does a fantastic job of explaining conventional superconductors.
Yeah.
But these high-temperature superconductors, they're a bit more mysterious.
So BCS doesn't really explain them?
Not completely. There are some aspects of BCS theory that might still be relevant,
Okay.
like the idea of electron pairing.
Right.
But the mechanism behind the pairing in high-temperature superconductors might be different.
So it's not just those phonons we were talking about?
Right. Might be something else.
Like what?
Well, there are a lot of different theories out there.
Okay.
Some people think that magnetic interactions might play a role.
Okay.
Others think that it might have something to do with the specific arrangement of atoms in the material.
Interesting.
And then there are some who think that it might involve some really exotic quantum phenomena.
Okay, so this is like uncharted territory.
It is. It's the Wild West of superconductivity research.
And that's what makes it so exciting.
Exactly. It's a huge challenge.
Yeah.
But if we can figure it out, it could lead to some truly amazing breakthroughs.
So much progress has been made with superconductivity, but there's still these big mysteries out there.
Right. It's like every time we answer one question,
Yeah.
10 more pop up.
Exactly. And high-temperature superconductivity is like the biggest mystery of them all.
It's the holy grail.
Yeah, imagine if we could get superconductivity to work at room temperature.
I mean, just think about it.
It would be revolutionary.
No more giant cooling systems.
Yeah.
Everything would be so much more efficient.
Like our electronics, our power grid, everything.
We could transmit power across the entire country with practically no loss.
That would be
It
amazing.
would be a completely different world.
So how do we get there? How do we unlock room temperature superconductivity?
Well, that's the big question, isn't it?
Yeah.
We need a better understanding of how these high-temperature superconductors work.
So what are some of the theories out there?
Well, one idea is that magnetic interactions might be really important.
Okay, so we're talking about the spins of electrons, right?
Exactly. Those tiny little magnets attached to each electron.
And how could that lead to superconductivity?
Well, some scientists think that under the right conditions,
Yeah.
these spins can actually interact in a way that creates an attractive force between electrons.
Interesting. So it's not the phonons, it's the spins that are bringing the electrons together.
It could be. It's still a very active area of research.
Okay. What else are scientists looking at?
Well, another really important factor is the lattice structure of these materials.
You mean like the way the atoms are arranged?
Exactly. The arrangement of the atoms can have a big impact on how the electrons behave.
So it's not just about the atoms themselves, but also how they're organized.
Precisely.
Never thought about it that way.
Yeah, it's kind of like how in a crystal,
Yeah.
the way the atoms are arranged
Yeah.
gives the crystal its unique properties.
Right.
Well, in high-temperature superconductors,
Yeah.
these complex lattice structures might create these little pockets where electron pairing is more favorable.
So it's like the lattice is providing a special environment for the Cooper pairs to form.
Exactly. And then there's this whole other realm of possibilities
Right.
involving some really mind-bending quantum phenomena.
Oh boy, here we go.
I know, right? So we're talking about things like quantum fluctuations
Okay.
and entanglement.
Yeah. I've heard of those, but they're still kind of fuzzy in my mind.
They're definitely on the cutting edge of physics.
So basically we're saying that these weird quantum effects might be playing a role in high temperature superconductivity.
Exactly. It's like the universe is using some of its most bizarre tricks
Yeah.
to make these materials behave in these amazing ways.
It's incredible to think about all this research that's happening right now, trying to figure out these mysteries.
It really is a golden age for superconductivity research.
And who knows, maybe one of our listeners will be the one to make that next big breakthrough.
Maybe they'll come up with a new theory.
Yeah, and we'll have them on the show.
Absolutely.
Okay, that's about all the time we have for today.
It's been a great discussion.
Yeah, I feel like I've learned so much about superconductivity.
Me too.
Yeah.
It's always fun to dive into these topics.
So to all our listeners out there,
Yeah.
keep those brains buzzing with scientific curiosity.
You never know what amazing discoveries are waiting to be made.
And join us next time for another deep dive into the fascinating world of science.